Welcome to AI Peer Review. Today we're diving into something that's, well, a real thorn in the side of AI development: hallucinations in multimodal large language models, MLLMs. These models are amazing, right? They understand images and text, but they often generate stuff that sounds totally convincing but is completely made up, not based on the image at all. So we're looking at an interesting paper today that proposes a really neat way to tackle this. Making these MLLMs more trustworthy is, crucial for using them out in the wild. But maybe first, why do they even do this? Why are they convincing fictions?
That's a great question. And maybe counterintuitively, it's often not because the model doesn't know something. It's more like, well, it's learned some bad habits. Behavioral biases picked up during training. You see, after pre-training on huge data sets, they go through fine-tuning. And some methods, especially around preference optimization, can accidentally teach them to prioritize sounding plausible over being, well, factually grounded to the visual input.
Ah, okay. So it's learning to be a good talker, or maybe too good.
Pretty much. It gets really good at mimicking preferred responses, even if the factual basis isn't there in the image.
And direct preference optimization, DPO, that's a big one for this kind of fine-tuning, right? It's used a lot.
It is, yeah. DPO is definitely prominent. It tries to align the model's outputs with what humans prefer, and it works to an extent.
Right. There's a catch.
There's definitely a catch highlighted in this paper. DPO, it seems, can actually make the hallucination problem worse in some ways because of how it learns.
Okay, so let's dig into that. What are the issues with DPO that this paper points out?
Well, the main thing is overfitting, but not in the traditional sense necessarily. It overfits to, like, superficial textual cues in the preference data.
Meaning, like certain words or phrases.
Exactly. High-frequency words, maybe a certain style of phrasing that appears often in the good examples. The model learns that pattern signals a preferred response rather than learning to check if the response actually matches the image content.
So it's listening to the rhythm, not the reason.
That's a good way to put it. The paper calls this distributional rigidity and creating spurious correlations. The model gets stuck on these text patterns, these spurious tokens, and doesn't ground itself properly in the visual information.
Right, okay. And the paper had that great example, didn't it, with the cat?
Yeah, figure 2C. It really makes it clear. You show the model a room, ask if there's a cat, even if there's no cat visually present.
The DPO model might just confidently say, yep, cat on the sofa.
Exactly. Just because cat shows up a lot in its preferred training responses, maybe often associated with sofas or rooms, the textual correlation overrides the visual evidence, or lack thereof.
Wow, and figure 2D kind of shows why this happens internally.
It does. It visualizes how DPO models can overattend, put too much weight on these spurious tokens. Could be common words, prepositions, generic objects that pop up frequently in the preferred text, even if they have zero connection to the specific image being looked at. This reliance on, well, static and sometimes superficial text signals makes the model brittle. Changes the context slightly, and because its cross-modal alignment isn't truly robust, it falls back on these learned textual patterns and hallucinates.
So the million-dollar question: how do you stop an AI lying so convincingly? This paper's approach, TARS, sounds quite different.
It is, yeah. TARS, MinMax, Token Adaptive Preference Strategy. The core idea is super interesting. It reframes DPO completely, turns it into a min-max optimization problem.
Like a game, the model playing against itself.
Kind of, yeah. It's designed to make the model more robust, more honest, by introducing this sort of adversarial dynamic internally during training. If you look at figure 3 in the paper, you get a nice visual breakdown. There are two main parts working against each other, in a sense. First, the maximization branch.
Okay, what's that maximizing?
It's maximizing token-level distributional shifts. Basically, it tries to shake things up, but importantly, under semantic constraints. It doesn't just create random noise. The goal is to simulate uncertainty, to simulate situations where the model's usual textual shortcuts might lead it astray. It does this by perturbing specific tokens what the paper calls visual agnostic tokens.
Visual agnostic, meaning words not tied to the image.
Exactly. Think articles like a, the, or maybe conjunctions, words that don't strongly point to something visual. TARS messes with these selected tokens, maybe by masking them or swapping them with synonyms.
And how does it pick which ones to mess with?
Ah, that's clever. It calculates a score for each token based on how relevant it is to the visual features of the image, the cross-modal alignment score. Then it picks the tokens with the lowest scores, the ones least grounded visually, and perturbs those.
I see. So it's targeting the weakest links in the text's visual grounding.
Precisely. As figure 2b suggests, this forces the model, during training to rely less on those superficial text patterns it might have learned and more on the actual visual evidence. It's like a stress test for its visual understanding.
Okay, that's the maximization part. What about the minimization?
Right, the minimization branch. This runs simultaneously. While maximization part is shaking things up with perturbations, this branch works to minimize the standard preference loss under those perturbations.
So it still needs to learn the human preferences, even with the noisy input.
Yes, but here's the crucial innovation. It uses something called spectral regularization, or LFRIC.
Mm-hmm.
This is needed because you have these dynamic perturbed inputs now, but the preference labels, like this response is better than that one, are static.
How does spectral regularization bridge that gap? Sounds complex.
It's a bit technical, but the core idea is neat. Instead of just comparing responses word by word, which could reinforce those spurious correlations again, it looks at the patterns in the model's hidden states. It applies a fast Fourier transform, an FFT, along the token sequence. Think of it like analyzing the rhythm or the frequency patterns of the model's internal representation of the response.
Like the underlying melody, not just the individual notes.
That's a perfect analogy. It aligns these spectral representations. This ensures the overall meaning, the semantic consistency, is preserved and aligned with preferences, but without rigidly matching specific, potentially spurious tokens. It allows for more flexibility while still enforcing factual grounding.
So the final TARS training combines the usual DPO goal with this spectral check for consistency, even when the input is being deliberately messed with.
Exactly. It's a combined objective, aiming for robustness and preference alignment in a much smarter way.
Okay, the theory sounds elegant, but does it actually work? Let's talk results. How did TARS stack up?
The results are, frankly, pretty impressive. They tested it on LIV 1.5, both the 7B and 13B parameter models. And a key point here, they achieved this using only about 4,800 public preference samples.
Only 4.8K, that's not much. No special expert labels or anything?
Nope. No expert feedback, no high-powered teacher models needed. That's a big plus for practicality, makes it much more accessible.
Okay, so let's hit the main target, hallucinations. How much did it reduce them?
Significantly. On the Ambier benchmark, looking at table 1 and 6, the 7B model's hallucination rate went from 35.4% with standard methods down to just 13.2% with TARS. That's a drop of over 22 percentage points.
Wow, that's huge.
It is. And on another benchmark, OBJ-HAL, which looks at response level CRs, they call them, it went from 54.0% down to 12.0%. Just massive improvements.
But did it sacrifice accuracy to get there? Sometimes models just become too conservative.
That's always the concern, right? But no, TARS seems to maintain factual consistency really well. It scored almost 89% accuracy in the P2E benchmark, which tests fine-grained reasoning, and on OBJ-HAL, the object-level hallucination rate was down to a tiny 3.2%.
So it's not just saying less, it's saying the right things more often.
Exactly. It's genuinely improving the grounding. And this ties into the efficiency point, again, using just those 4.8K samples. It outperformed other methods like OPDPO that use the same amount of data. On the 13B Amber test, it boosted object coverage by over 11 percentage points compared to OPDPO.
And it scales okay. Works on bigger models, too.
Yep. Showed consistent gains moving from 7B to 13B parameters. And get this, as performance starts getting really competitive with some of the big proprietary models.
Like GPT-4o.
Yeah. The 13B TARS model nearly matched GPT-4o on object coverage in Amber, 59.8% versus 60.9%. But here's the kicker. TARS actually had a lower hallucination rate than GPT-4o on that benchmark, 12.7% versus 17.6%.
You'd beat GPT-4o on hallucination rate.
On that specific test, yes. It also outperformed DeepSeek VL2 27B. So we're talking serious performance gains here, making open models much more competitive in terms of reliability.
That is impressive. So what's happening under the hood? Why is TARS so much better at this? You mentioned the latent space.
Right. Figure 5 gives a great visual clue. It's about disentangling things. With standard DPO, the model's internal representations, its understanding for hallucinated outputs and genuinely preferred outputs get all mixed up. They form these entangled clusters.
Because it's latching onto superficial signals that appear in both.
Precisely. TARS, on the other hand, creates a much cleaner, more structured latent space. The representations for hallucinated outputs are clearly separated from the ones that are correctly aligned with preferences and visually grounded.
Ah, so it learns to cleanly distinguish factual preferred responses from plausible but false ones?
That's the idea. It learns a more semantically faithful representation space, reinforcing only the truly grounded responses.
Okay, this makes sense. But TARS has several components. The perturbations, the way it selects tokens, the spectral thing. Which parts are really doing the heavy lifting? The ablation studies must shed light on that.
You do, yeah. Table 2 breaks it down nicely. If you remove the token level perturbation, the TP part,
The part that shakes things up.
right, if you remove that, cognitive inconsistency shoots way up. The cog metric jumps from zero point 0.4 to 2.5. It shows how vital that perturbation is for actually exposing the model's reliance on those spurious text patterns.
Okay, so perturbation is key. What about how it picks tokens? The cross-modal alignment score, CAS.
Also crucial, if you take that out so perturbations become more random instead of targeting visually agnostic tokens, hallucination rates go up quite a bit. It shows that targeted perturbation is much more effective at suppressing those spurious links without harming general understanding.
Makes sense. And the spectral alignment, SBA.
That unique frequency-based check. Removing it also led to a noticeable jump in hallucinations, around 1.9 points overall, and also worsened fine-grained object hallucination. It really suggests that this frequency-aware consistency check is important for solidifying that fine-grained factual grounding.
And I guess finding the right amount of perturbation and spectral regularization matters too. Not too much, not too little.
Absolutely. Table 4 and 5 show that. Too much perturbation can break things, too little doesn't help enough. Same with the spectral weight. There's a sweet spot. And Table 7 reinforces a key point. This spectrum-based alignment in TARS is better than trying to do more rigid token-level contrastive alignment. That flexibility in the frequency domain seems really important for robustness.
So let's wrap this up. TARS seems like a really significant step forward. It's this clever, lightweight strategy reformulating DPO into a min-max game.
Yeah, and the results speak for themselves. Major reductions in hallucinations, achieved efficiently with minimal public data.
By forcing the model to deal with uncertainty and align itself using these spectral patterns, it encourages reliance on what's actually in the image, the causal visual cues, not just text tricks it learned.
Exactly. It's a promising path towards MLLMs that aren't just plausible, but are genuinely more trustworthy and grounded in reality. Especially valuable where you don't have tons of expert data to throw at the problem.
Which brings us to our final thought for you, the listener. Given TARS's success in getting MLLMs to separate what's truly seen from what's merely plausible, how might this kind of approach reshape our expectations for AI systems that need to reason critically and reliably about the world around them?